Hey there, scientific brilliant people. How are you today? So today I'm going to explain the energy work power chapter for grade 8 in nutshell. So let's begin with the work first. Now people, work, what do you mean by work? So when displacement takes place in the direction of force, work is said to be done. Correct? Now let's look at the formula first. So the work done formula is given by work is equal to F into D. FD cos theta is not there in our course, so I am just going to brief it very simple over here. So force, this is the formula. Now if we look at the SI unit of force is Newton, SI unit of displacement and distance one and the same thing, because when a body is moving in a straight line, distance and displacement are same. So SI unit is meter and Newton into meter is called joule. So joule is the SI unit of work done. Now if I talk about the CGS unit of force is dyne, CGS unit of distance is centimeter, dyne into centimeter is called erg. And now this is the CGS unit. Now if I just give you the conversion, 1 Newton meter, that is 1 joule, and 1 dyne into centimeter, that is equal to 1 erg, and 1 joule is equal to 10 to the power 7 erg. Just remember these people. Correct? Okay, let's move on now. If I substitute, if force is equal to 1 Newton and if displacement is also 1 meter, that means work done is equal to F into D, that is equal to 1 Newton into 1 meter, that is equal to 1 joule. So how can you actually define 1 joule? So when 1 Newton force applied on the body creates a displacement of 1 meter, then the work done is said to be 1 joule. Suppose this is a body and this body is being pushed with a force of 1 Newton, and suppose this body travels a distance of 1 meter, then the work done in this situation is said to be 1 joule. Correct? Okay. Now let us consider a few cases in which the work done is 0. So now we will take the cases where the work done is 0. Zero work done cases. Now when can a body have 0 work done? Suppose in first example there is a wall and then a boy is pushing the wall with, say, force F is equal to 100 Newton, and the wall does not move because the wall is very strong. So that means work is equal to F into D, but F is 100 Newton, agreed, but there is no displacement as the wall is not moving. So this is 0 meter. Under that situation the work done is said to be 0 joules. Second situation, now let us consider sun at the center. This is sun and here is earth, and the earth is being pulled towards the sun with a force F, that is called gravitational force. And when the earth completes one full revolution, then the earth again comes back to the same point. That means the displacement is again 0. So work done will be equal to again F into D, and again this time the D is going to be 0, so the work done is going to be 0 joules. So these are two examples in which the work done is 0. Again we can take a third example. Say a man is carrying a load on his head and he is stationary. That means suppose the load is 50 Newton weight. Now this load is not falling down. That means the head of the man is applying same force in the upward direction. So the force applied by the man on the block is 50 Newton. Now the man is standing, so the man is not moving. So if the man is not moving, the block is also not moving. Again, displacement is 0, work done would be 0. Correct? Okay, so now let's talk about the types of energy and energies. So people, energy, in our energy chapter, we are supposed to discuss about kinetic energy, potential energy, and the sum of kinetic and potential is called mechanical energy. Right? Now let's talk about the kinetic energy very fast. So kinetic energy is the energy possessed by the body due to the motion. So correct, energy possessed by the body due to motion. And now kinetic energy is, so kinetic energy K, it is represented by Ke. Now kinetic energy formula is half into m into v square. That means we can consider a man moving with speed v, so v is the speed, actually velocity, but since the man is moving in a straight line, velocity and speed are same, and the mass of this man is m. So this half is an additional factor. You cannot remove this half from the formula. This is given formula. So kinetic energy depends upon mass and square of the speed. So if you want to find out the SI unit, half does not carry any unit. SI unit of mass is kilogram, speed is meter per second, and the whole square, which means kg meter square upon second square. Now people, kg meter square per second square is also called joule. So if you if you see this carefully, then this is also joule, the SI unit of energy, and the SI unit of work is also joule, right? So work and energy, they share same units. In the same way, if I talk about the potential energy, so potential energy is represented by PE, that is the energy due to shape or position. That is potential energy. So potential energy is present mostly in springs, and potential energies are again of two types. One is gravitational potential energy and elastic potential energy. Right? So let us talk about the gravitational potential energy first. Elastic potential energy formula, we don't have it in our syllabus. So let's draw a situation very fast over here. Suppose this is a ground and we have two small hills. Like this, and two people are standing on the hill. Say the mass of these two persons are same, that is m is equal to 5 kilogram or m is equal to 5 kilogram. Now the height of this man above the ground, this is called h. Height of this man above the ground, this is called h. Now here in this case h is say 1 meter, here h is say 10 meter. Now potential energy formula, people, that is given by potential energy PE, and this is gravitational potential energy, this mgh, where m is the mass G is acceleration due to gravity. If it is not given as 9.8, you can always choose to take this as 10 meter per second square. H is the height above the ground. Now let us calculate, suppose this is situation A, this is B, and if I calculate the potential energy in situation A, that is equal to M, that is mass is 5 kilogram, G is 10 meter per second square, H is 1 meter, so it is 5 into 10 into 5, so that is 50 kg meter square upon second square, as we have just now discussed, is called joule. So whether it is potential energy or whether that is kinetic energy, the energy unit always remains joule. Now potential energy in case B, that is equal to 5 kg into 10 meter per second square into the height is 10 meter. So this is 5 times 50, 500, answer is joule. So that means people, more the object is high above the ground, more will be its potential energy. So now let's talk about the another energy, that is elastic potential energy. So suppose if you have a spring or a rubber band and say the rubber band is this long and this is the natural length of the rubber band, people. So its initial length itself is L0. We are not doing anything. Now I am extending this rubber band, so I am applying force in the outward direction and the rubber band becomes long. So that means there is some amount of work done by me because I applied the force in the opposite direction. Rubber band doesn't want to increase in the length, but still I had to do lot of work in extending it. So the amount of energy lost by my body in doing the work, that energy goes inside this rubber band, which is pulled in form of potential energy. So this rubber band will have stored energy in form of potential energy. And how did it gain it? Because I had to do some work, so my body lost energy. I got tired in doing that, and the energy from my body went inside the rubber band in form of potential energy. Now suppose if you have a spring and this is the spring at its natural length. Its natural length is L0. You are doing nothing. It is as it is. If I compress it by exerting force in this direction, then the shape of the spring would be like this. And in doing that, I had to do the work. My body lost energy. That energy got stored inside this compressed spring in form of potential energy. So compressed or stretched rubber band or spring possesses elastic potential energy. Its formula, people, is half K square, but K is spring constant. Again, we will not get into that discussion. Just remember this, right? Okay. Next topic is called the law of conservation of energy. So here we have an inclined plane. You can consider this as a small hill which has got inclined plane, and a small ball is placed over here, people. Now this ball is at, say, height 10 meter above the ground, and this ball is at rest. So that means this place is A. Now this ball is being given a very gentle push, but the ball was at rest, people. The speed of the ball was 0 over here. So that means kinetic energy is half mv square, in that v is 0. So the kinetic energy is 0. Now if I find out the potential energy, that potential energy is mgh. So g is, it is not given, so we'll take that as 10. Mass of the ball, let us take mass of the ball as 10 kilogram. So 10 kilogram, acceleration due to gravity 10 meter per second square, height is also 10 meter. So that means 1000 joule is the potential energy. And, and the mass of the ball we have taken here as 10 kilogram. G is 10 meter per second square, and this is point A. Now the ball comes down rolling like this, and finally the ball reaches over here. So this is, say, point A, this is point B, and I'm neglecting this one and I'm considering this as point C. If I find the total energy is sum of kinetic and potential, Ke plus Pe, and if I add the total energy, I will get the answer as 0 plus 1000, that is 1000 joule. Now people, law of conservation of energy states that if there is no loss of energy, if there is no friction, then the total energy at this point, this point, this point, or this point, wherever, it remains the same. So at this point, suppose if I give you this height as 5 meter, I don't know what is the speed, so I don't know what is kinetic energy of the ball, but I do know that potential energy is equal to mgh. M is 10, g is 10, h is 5, that is 500 joule. But the total energy again at point B is 1000 joule as per law of conservation of energy. So if 500 is potential, then the rest 500 has to be the kinetic. Right. Now when we reach over here, the ball is at height 0 above the ground. So that means the potential energy, I don't know what is kinetic energy, so I am leaving it blank. But I do know that potential energy is mgh, out of which h is 0, so potential energy is 0. But still the total energy is constant. So that means the entire energy is now kinetic. So if you look carefully, people, here as the ball descends down, the height of the ball above the ground decreases. So potential energy decreases. As you can check by yourself, earlier it was this, then this, and finally became 0. But on the other hand, if you look carefully, the kinetic energy keeps on increasing. So here the total energy remains same. So potential energy as the ball goes down converts into kinetic energy. So here highest potential energy, 0 kinetic energy. Here highest kinetic energy in 0 potential energy. But the sum of the energy keeps on remaining constant. So this is the law of conservation of energy, people. Now this is a very good example in which we can say that the potential energy getting converted into kinetic energy. Now let's take a similar situation. This was, say, case A. Now let's take case B, in which I am going to draw a simple pendulum. Okay, so here we have a simple pendulum, this one, and if I give a gentle push, to this pendulum, the pendulum starts oscillating. This is position A, B, C. A is called mean position, resting position, whereas B and C are called extreme positions. Now people, what happens is, when you give a gentle push, this pendulum goes high. That means the height of the pendulum above the ground increases and the speed decreases. Speed decreases, becomes 0, and finally it stops. Again speed increases, becomes maximum. Again speed decreases, becomes 0. So point B and C are the point where it reaches the highest height. So at B and C, the pendulum will be having highest potential energy, because the height is maximum. But at point A the height is 0, but the pendulum would be at the highest speed, so it will have highest kinetic energy. So here people, the kinetic is 0 because the pendulum comes at rest, so kinetic is 0, but potential is maximum. but the sum remains constant. Say it is 10 joule, this is 0, so total is 10. Now when this comes over here, the total energy is only kinetic because here potential becomes 0. And again on the same side. So speed increases, becomes maximum, becomes 0. Again speed increases, becomes maximum, decreases, becomes 0. So kinetic energy at the extreme position, because at the extreme position it cannot go further, it has to stop and turn back. That's why the speed is 0. These are the two typical examples in which kinetic and potential are continuously getting changed into one another. So now let's move on with a next example of energy conversion. Till now we were discussing about the conservation of energy, and we were also discussing about the potential to kinetic conversion. Now let's talk about electrical energy. And that electrical energy getting, say, converted into heat and light. So people, this is an example of typical bulb. So in bulb what happens, the moment you switch on, it draws the electricity. So the electrical energy, it gets finally converted into light energy, but there is also a wastage of energy in form of heat, right? Then let's take the example of chemical to electrical. The answer is, guess it, yes, the answer is battery. Now in battery, we have, say, some chemicals, and the chemicals contain bonds. Now due to the chemical reaction, the bonds break and chemical energy is released. So even if you don't do anything, there is a chemical energy stored inside. Now that gets converted into, suppose if you put a bulb, so that gets converted into electrical energy, and finally from there the bulb emits light and heat energy. So electrical energy is being obtained from the chemical energy, right? And then this one finally converts into light and heat. Okay, now if we have a car fuel, say an example of car, if we have this car, now this car has got engine, suppose here. Now this engine has got fuel. Fuel is, say, diesel or petrol. Now it's a chemical, and chemical contains bonds. So fuel contains energy stored in bonds. That's why we call this energy as chemical energy. It is already stored inside. Now when the petrol goes inside the burning chamber or the fuel chamber, first of all petrol burns. So that means the chemical energy is converted into heat energy because it burns and heat is released. Then there are gases, and gases expand, and then the piston starts moving. So finally into kinetic energy. Right? Okay. So these are few of the examples of the energy conversion. Now let's talk about the final chapter, final part of this topic, and that is power. So let's discuss about power now. Power is again work done upon time taken, or it is also written as energy upon time taken. Now this is the formula, people. If you want to make a definition, if you see any time at the bottom in the denominator, you can always say rate. Suppose we know that distance, okay, speed is equal to distance upon time. Then I can also say that rate of distance, rate of change of distance is called speed, because whenever you have anything, any quantity like time in the denominator, the rate will come. The word rate itself means in the denominator there is time. So here also I will write rate of doing work, rate of doing work, or rate of spending energy is called power. This is one definition, people. Now if I write the another definition, if I make this time as 1 second, then power and work will become equal, because in denominator we have 1, so that means this entire fraction is the work only. So power is work done by the body in unit time. Unit time means 1 second, correct? Okay, and now if we check the unit, then power is equal to work or energy, that is joule upon second, and joule upon second is called watt. Correct, people? So this is the SI unit. So if I want to write down power of a body is 100 watt, then power of a body is 100 W, capital W. This is how we write it down. Correct? Now let me give you a very easy example of a power. So here there are two situations. This is situation B, this is situation A. Now in situation B, a block is being pushed in this direction and the block reaches over here. And suppose the block moves by distance 10 meter and the applied force was 100 Newton. Here the same block exerted by same amount of force reaches the same distance. But this block completes the journey in say 1 second. This takes 10 seconds, correct? So due to the application of this force, suppose it takes, due to high friction over here, it may be taking less amount of time. So this reaches over here in 1 second. So if I want to calculate power, power is work upon time. Work is force into distance upon time. That means 100 into 10, that is 1000 joule, that is the work done, divided by 1. So this is 1000 joule upon 1 second, that is 1000 watt. Correct. Now over here, the power is equal to power in A and power in B, that is equal to, so power in B, that is equal to work done, again work upon time, that is equal to F into D by T. F is again 100 Newton into 10 meter. So 100 into 10, that is 1000 joule upon 10 seconds. My answer is 100 watt. Look people, that means if you want to do the things faster, you have to use more of your body energy in less time. So in both the situations, work done is same. If you look carefully, work done in A and work done in B are same, because it is 1000 joule. But lesser the time, power would be more, because power and time are inversely proportional. Correct? So we have concluded the entire chapter. Hopefully you got it. And one last point, power, work, energy, all are scalar quantities. Whereas force, displacement are vector quantities. They have direction, these three doesn't have direction. So guys, hopefully you have enjoyed the explanation and do score well in the test, and thank you for watching the video.